It's my pleasure to both welcome and introduce Ignas Snellen. Now, you may notice the topic is a little odd for me to be introducing the speaker, but I've known Ignas now for about 20 years. He was a graduate student in Leiden when we overlapped. I was the Nobel Fellow and he was a graduate student. And we actually used to work on radio galaxies together. And I remember because he invited me to come to Leiden, he's from Leiden University, to be on the thesis committee of his last student working on radio galaxies. He just told me, he said, it is such a nice feeling not to have to work with you guys anymore on radio galaxies. Planets are so much nicer. So anyway, so it's my pleasure to introduce Ignas Snellen. So Ignas was a graduate student in Leiden. He then did a postdoc at IOA in Cambridge and then up in Edinburgh. And then returned to Leiden as a professor, where initially I think you started half LOFAR, half planets.
I did, yes.
And then as soon as he had tenure and he could move out, you don't do LOFAR anymore, I guess.
No, not really, no.
And today he's going to tell us about his planet research, exoplanets and the search for extraterrestrial life. Ignas, the floor is yours.
Thank you, Matt. Is my mic working? Can you all hear me? Yes? Okay. It's very nice to be here. Last time I was in this room was about three years ago when you had your annual workshop here. And it was so warm that I almost fainted. So I'm very happy it's a much cooler day now. So I'm going to talk about extrasolar planets. This is a very exciting field. Yeah, when you have been working in this field for a while, like me, then you start to forget that only about 25 years or so ago, the only planets that we knew were the planets in our own solar system. And then in 1992, the first planets in pulsar systems were actually found. And yeah, the field really started off in 1995 with the first radial velocity planet, 51 PAC-B, which orbits a solar type star. And then, yeah, it's really, you can see here, I sort of indicated the important milestones over the years, the actual planet, the first planet transits that led to the first measurement of an actual atmosphere, the first planet thermal emission in 2004. Then we started to move from hot Jupiters also to smaller planets. The first Neptunes were found, a first thermal map, a direct image in 2008. And then we also go to other molecules and winds. And then in 2013, about 5 years ago, we reached the milestone of about 1,000 planets. And then I'll show you a little bit more later, only less than 2 years ago now, the first exo-Earth was found. So what is driving this exoplanet revolution is not that we are becoming smarter and smarter, but that's because our instruments are getting better. If you only already think about radial velocity measurement over the course of about 30 years, the actual accuracy with which we can do radial velocity measurements has actually increased by about a factor of 1,000. And that is really driving the field, and therefore we can also look forward because we sort of know what the next decade is going to give us with respect to new instruments. And there are two very important milestones there. There will be the launch of the James Webb, if that will ever happen. This is an old slide. You can see I still have it there optimistically in 2020. That will, of course, move a little bit more into the future. And then very important for my work will be the ELT, which we hope will see first light in about 7 years from now. And this really, I think, will move us into the part from not only measuring atmospheres of Neptune and atmospheres of Earth, but also into the range where we can start to probe biomarker gases and see whether there are any other planets like the Earth and see whether they actually harbor life. I hear my mobile phone going off. That's probably a good idea to put it out before my mother calls me or something like that during the talk. Okay, so let us first go through the what are the main questions of this field. Why do we want to study extrasolar planets? Well, it's all about placing the Earth and our solar system in the context of all planets in the Milky Way and the universe. And we have some general questions. How do planets form? What ranges of architectures of planetary system exist? Now, is the solar system typical? Or do we really live in some sort of a special place? But I really like this final question here. Now, do other life-bearing planets exist? Or is the Earth sort of unique in this way? But first, before we go on and talk about exoplanets, it's maybe good just very briefly, very briefly, look at the planets, of course, where we know most of, and that are the planets in our own solar system. What we actually already immediately learned from the solar system, looking at the ensemble of planets, that they show an immense complexity and diversity. For example, we have the exogiant planets. These are molecular hydrogen dominated. They are dominated by clouds, strong zonal flows. They have these storms like the giant red spots, which has been raging for hundreds of years. Then we go to the more, when we go to the rocky planets and look at the atmosphere there, we see, a very clear signs of diversity. Now, if we look at the planets and the moon, where we see an atmosphere, we see Venus. This is a super rotating CO2-based atmosphere. It has these strong opaque sulfuric acid clouds. Then we move to the Earth. Same mass, same radius. It's partially clear. It's nitrogen-based. It has a large fraction of biotic oxygen. And then when we go to Mars, that has, again, a CO2 atmosphere, very thin, and has, for example, a trace amount of methane, of which we don't know the actual origin yet. And then when we look at Saturn's moon, Titan, there we again see it is a nitrogen based, where we see opaque methane and ethane clouds. And they have also not a water cycle, but a cycle of methane and ethane on this moon. So I think it will be very difficult if we would only have the solar system and come up with a general theory of planets, identify different families and see what is the origin of these different atmospheres. Of course, you can make up theories why these differences are there, but how do we know that these theories are right? And I like to make I show an example, and the way I see this, it's like one of my heroes is Charles Darwin, and it would be the same as if Darwin had to find out the actual tree of life when he would only have access to three or four animals. Now, how do I link this monkey to this owl and to this scorpion? I think with just 3 animals or 3 species, this is not possible. And he also recognized this, so he went on this epic voyage on the Beagle, went to distant shores and islands, find out about all these different families of plants and actual animals. And only in this way he came back with his great theory of evolution. And I see the exoplanet science also a bit like this voyage. It will be very difficult. It will be very hard to study exoplanets, but we really need it to actually understand the general formation and evolution of planet systems. So we have now about 25 years of exoplanet studies. So what have we learned so far? Well, typically about more than 1,000 exoplanets have been found. They are very common. And immediately we see that the actual diversity is even larger than we see in our own solar system. Now, we have, for example, the hot Jupiters, gas giant planets in very short orbits. We have no idea, well, we are quite sure that they haven't formed at such a short orbital distance, so they have to have formed much further away from the exostar and in some way have migrated inwards. Then we have this typical class of super-Earths, or mini Neptunes. Also a type of planet, very common, but it's not seen in our own solar system. And then we have these super Jupiters, these very massive gas giant planets that are at very large optical distances, orbital distances, up to 100 AU or even further. And also for those, it's not clear how such planets could actually form. Now, we typically see that for solar-type stars, about 1 in 10 stars host a Jupiter-mass planet, so maybe that fraction is actually a little bit higher. We have about 1 in 5 stars host a Neptune-mass planet, and we see that most stars host an Earth-mass planet. So I'm not talking here about Earth-like planets, no, I'm not talking about planets that have oceans and trees and things like that. It's just a simple parameter that the masses of the planets are about that of the Earth, but they could be at any orbit. Now, what I think it is, of course, in the end, at least with my research, we hope to zoom in on trying to identify planets where life is possible and maybe see whether there is actually life on such a planet. But I also want to say that to be able to do this, we must have a much broader understanding of planets, their atmosphere, how they form and how they actually evolve. Only by understanding the atmospheric processes and their evolutionary history, it will in the end be possible to actually unambiguously identify extraterrestrial life. And what I mean to say by that is, at some point, I hope in the next decade, we will identify planets where we see, for example, oxygen, and we know on the Earth, oxygen is due to life, but yeah, that doesn't mean that on another planet this oxygen is actually due to life. We can only find out after we really have understood all the atmospheric processes that can happen in such a planet before we can really identify it to be due to biological activity. And this will be a very difficult and long path where many different disciplines from biology, atmospheric physics, geophysics have to come and work on these type of problems. Okay, the great news is that also in recent years the progress has been quite amazing. We now have started to have a sample of planets about the size or mass of the Earth that seem to be in the habitable zone of their star, meaning that possibly liquid water could be present at their surface. First of all, there's of course Proxima b, found about 1.5 years ago with the HARPS spectrograph. It's in an orbit of about 11 days. But because Proxima b is such a small and faint star, an 11-day orbit means that it receives about 30% less energy from its star than the actual Earth does. But that's still more. That's still about 60% more than actually Mars does. So it should have a climate somewhere in between that of Mars and the Earth. Now, of course, we don't know whether life could actually be present on such a planet, because the actual star is not so nice. This Proxima sends out flares. There are all kind of problems with the actual history of such a star, that in the early history of Proxima it should also be radiate a lot more energy, and therefore it should have been a lot hotter. The exoplanets are locked, so there's always one day side and one night side on such a planet, so it's not clear whether life could actually exist on Proxima b, but still, this is such a great sample to start looking and see what kind of climates what a climate is actually present on this planet. That we can really start doing this in the next decade. Well, it turns out that these rocky planets are very common around nearby M dwarfs. This is very nice work on Proxima b. They have a nice website. It's the pale red dot website, where you can see live the radio velocity points coming actually in. And they have another, a half year ago or so, they had another session on Proxima. And there may also be an actual evidence for a second planet, so there could be a Proxima c. There's also some other work of the nearby star Ross 128, which also shows to have a rocky planet. Now that's all radio velocity work. There's also the transit work. This is also some work that you get really jealous of when you see it. This is, of course, the TRAPPIST 1. Now, this team really went out, starting a couple of years ago. What if the lowest mass stars, so we're talking about an M8 or even high mass brown dwarf stars, do have planets? Right? Shouldn't it be much easier to actually see them using transits? So they started to monitor about 50 stars, and already within a couple of months they found TRAPPIST 1b. So they found the first planet, and I think they also found TRAPPIST 1c. And then they got a lot of Spitzer time. I think they got 30 or 40 days of Spitzer time where they monitored the whole system, because next to TRAPPIST 1, B, and C, they found a single transit, and they thought, hey, that's so, there must be a third planet there. So they monitored for a month or so, and they found 7 planets, all very nicely aligned. You can see the extra-orbital periods here. It's ranging from 1.5 days to about 20 days. They're all about the size of the Earth, and if you think about how much energy they receive from that star, this is the incident flux here on the horizontal axis. There are about 3 or so, 3 of these planets that are in the so-called habitable zone that could receive so much energy that they could have liquid water on their surface. So this is all really very exciting, and again, hopefully in the next decade or so, we can really probe the atmospheres of these planets and see what they are actually made of. Also, what I really like about this system is that they found it only out of a very small sample, meaning that either they are very lucky or this kind of planet systems are very, very common, because you have to have the right orientation to see these planets transits. There is only about 1 in 40 or so chance. So if you would have a random orientation, and they only found it out of a sample of 50 or so stars. So that basically tells you that these planets are very common, and we will soon learn that from this group who is observing now a larger sample. And that these planets are coming, we know that also from Proxima b, because our nearest star has actually a similar planet as these. Now, this is all so far all about finding planets. My work is more about trying to learn about the atmospheres, and there the game is somewhat different in the sense that I've told you that thousands of planets have been found, but for most of these, not a single photon has been identified coming from the planet themselves. Yeah? If you do radio velocity methods work, even if you do transit work, it's not that you see photons from the planet. Well, if you do atmospheric work, you no longer cannot do that. You have to separate light out that is coming from the star and coming from the planet. And there are basically 2 families of methods to actually do this. I call them a time differential method and an angular differential method. You could also simply say one is sort of the actual transit method, and the other one is the direct imaging method. So the direct imaging method, you spatially separate the starlight from the planet, and sorry. Yeah, it's still working. This is a very nice example. It's at this point still very difficult to get the contrast because the expected contrast between the star and the planets are very high, but not so much for the very young systems, so typically 10 million years old. This is an example. This is a young A star, HR 8799, and you really have a family portrait of 4 giant planets here. And it's nice now over the course of several years you really see the exoplanet move around the star. So that's one way. That is the angular differential method. The time differential, we are talking about transits and eclipses and phase curves, and that makes what happens there is that as function of time, we see the planet light differently. So for example, only during the actual transit, you see the actual starlight filtering through the atmosphere of the planet. And I have a slide here. Is there a pointer which I can use, or? Oh, here it is. I see a big stick. It's all right. Yeah, it's physical. I like it. Yeah, it's good. So what happens when the planet orbits the actual star? At the moment the planet moves in front of the star, of course some starlight is blocked by the planet, but also some light filters through the atmosphere and leaves an imprint of atomic or molecular absorption or scattering processes. Then half an orbit later, the planet is actually eclipsed. That is, so for a moment we don't see the exoplanet light, so the light missing, that could be reflected light, or that could be direct thermal emission from the planet. We can actually measure in that way. And then what can happen is if we monitor a system, then we can really see the phase variations, meaning that near the transit we look at the cool night side of the planet, and then near the eclipse we see generally the hotter day side. So that can tell us something about the temperature structure around the planet. Just to give you a short intro of what we actually measure when we take transit spectra, it's basically the effective size of the exoplanet moving in front of the star. So if we observe it at a certain wavelength where the atmosphere absorbs, then the absorption of the atmosphere makes this planet size a little bit larger, and therefore it seems that the actual transit at that wavelength is actually a bit deeper. So when we plot the transit, the actual transit spectrum, like here, we see here the radius ratio, but what we actually measure is the transit depth. So the transit depth as function of wavelength. And this is, there are 2 planets with which we can do this very well. That's 2 hot Jupiters, HD 189 and HD 209458. So you see both examples here. So this is a transit spectrum, very famous, where we see in the UV optical that the effective radius of the planet is significantly larger, and we think that this is due to Rayleigh scattering of haze particles high up in the atmosphere, and then it sort of flattens out. Now these observations, they don't really show any other absorption features, but maybe a cloud deck, but there's also now some actual molecular features are seen there. For example, water, and this is a nice example of HE 209. The blue dots is the data here, so again this now says absorption, but this is actually planet radius, or it is transit depth. And you see very nicely, so there's no variation in transit depth here, and then around 1.35 micron it shoots up, the planet is larger, and that is because of extra absorption in the atmosphere due to water. Now in this way water is seen also now for an whole ensemble of planets at about 12 or so hot Jupiters. This is seen, both the Rayleigh scattering slope and the actual water absorption. And what is very nice is what this is David Singh's work, who used to be here in Paris, I think, what they observe is that when you don't hardly see any Rayleigh scattering slope, there seems to be a strong water feature, and if you have a strong Rayleigh scattering slope, the water feature is much more muted. You can see that here. This is sort of the Rayleigh scattering, a measure for the Rayleigh scattering slope, the prominence of the Rayleigh scattering slope, and this is the water absorption. And the idea here is, and I think now we're really starting to learn some physics about in the atmosphere of these hot Jupiters, is that when you have a strong Rayleigh scattering slope, that means there are hazes high up in the atmosphere that mute the actual water signature. So yeah, and you have strong hazes, you don't see the actual water. If the atmosphere is clear, sorry, if you have strong hazes, you don't see the water. If the atmosphere is clear, you see a strong water feature. So the variation is probably not caused by different volume mixing ratios of water in these planets. These planets are probably all very, very similar, but it's just one has hazes and the other one don't. Still, we don't know why some planets have hazes and others don't, but that's a whole new question. Now, several groups have started to move away from hot Jupiters and going to cooler planets. This is easiest done when these planets orbit small stars, and that's because the actual ratio between planet and star is then significantly larger. This is an example of GJ1214. It's sort of a super Earth or a mini Neptune. And the nice thing about these, this is basically a new class of planet, and we can basically we can solve for the mass-radius relation in two ways. Either these are volatile-rich planets, so they may be very water-rich, or these may have a rocky core with a hydrogen envelope. Now, how could you measure the difference between these two? How could we find out what the difference? Well, if the atmosphere is water dominated, then the scale height of the atmosphere is much smaller, and you would expect much muted signals, transit signals, while if it was a hydrogen atmosphere, you would expect very strong signals. And that is what you see here. This is what you expect the variations from water in a hydrogen atmosphere, and this is for a water-dominated atmosphere. And when you zoom in, you see actually that the data is very flat. You don't see anything. And so even for a completely water-dominated atmosphere, you would expect a much stronger signal than is seen. And the general idea here is that there are actually clouds that are very strongly muting the actual atmosphere. So this is one of the challenges that we will face in the future of this kind of atmospheric work. Now, I don't have time for this. I want to say a little bit about the future. This type of work works very well from space. There is, of course, the James Webb is going to be launched soon, but also very exciting Ariel. I understand the IP has a very strong role in this mission, and we're all very happy that it got selected by ESA, and it will really observe a very large sample of these warmer objects. Okay, now I'm about halfway in my talk, so I want now to talk about our own work. This was a general overview of the field. In my group, we really focus on trying to do these atmospheric studies from the ground. And what we have found out is that both the transit method, so the time differential method, as the angular differential method, work very well if you combine them with high dispersion spectral observation. And the idea behind that, so by the time difference between the signal from the planet and the star, you can already separate out the planet from the star. But what helps if you then get an extra measure, and that is the spectrum, because you also expect the spectral lines of the planet to be very different from that from the star. So in that way, you can actually have an extra measure to separate out the light coming from the star and from the planets. In the same way from the high contrast imaging, that because these two spectra are different, you can actually use that to probe much deeper into the stellar halo. And I'll show you later some actual examples of this. So how does this exactly work? With high dispersion spectroscopy, I mean we typically work with resolving powers of about 100,000. And when we probe then a molecular band, we don't probe the band as such, but it's really we resolve the band into tens or even hundreds of individual lines. And what is important, we then become sensitive to strong Doppler effects due to the orbital motion of the planet. So we're not talking about the Doppler wobble of the actual star, which can be tens of meters per second. No, we're talking about the orbital velocity of the planet. For the Earth, this is 30 kilometers per second. For hot Jupiters, this is up to 150 kilometers per second or even more. And what that means is, if you observe a star for a couple of hours, that the component of the radial velocity changes. So the Doppler effect changes, and these planet lines, they move through your spectrum over the course of a night, and you can use that movement to basically filter out anything else that does actually not move during the night. For example, the lines in our own atmospheres and any stellar lines. So this is just a toy model of carbon monoxide, how this would work. This is orbital phase, and this is wavelength. In white are the planet lines, so they change in radial velocity. Here is the transit data, here is the thermal emission data. You don't see it here because normally the ignite side is cooler, therefore the lines are much weaker. And what you also see during the secondary eclipse, yeah, you don't see any planet light. So although before, like the James Webb and Ariel will really use the fact that you have planet light just before and after the secondary eclipse and not during the eclipse to measure the planet light. In this case, you actually cannot use the secondary eclipse light, and therefore we don't have to do this for only transiting planets. We can basically do this method for any planet that is bright enough. Okay, the first example I want to give is of a transit spectrum. So why is this slanted? Well, if we take the orientation in such a way, you have the star here, the planet, the Earth is in this direction. When a planet moves in front of the star, it doesn't do that in an actual straight line. The orbit is a bit curved, meaning that in the beginning of the transit, the light is a little bit blue shifted because the star is moving towards you, or the planet is moving towards you, and the end, the planet is moving a little bit away from you, and that's why this line is slanted. And the way it's orientated tells us what the orbital velocity of this planet is. So we did this already a couple of years ago, and this is now. So what we do is we try to actually remove any stationary part of the exospectrum. We have a residual spectrum as function of time, and in that we do a cross correlation method to search for the CO lines in the exospectrum and add up the signal from all the individual lines. And this is what you basically see. This is the cross correlation signal as function of velocity and as function of time, of orbital phase. And you see already there's a faint hint here. This is offsetted from 0, and that's because of the system velocity of the star and the barycentric velocity of the Earth. If you then put it in the rest frame of the star, you get actually this, and you get indeed this actually slanted line. And what is now nice is that this orientation gives you the actual velocity of the planet around the star, and because we already had before measurements a decade earlier of the orbit of the star around the barycenter itself, so we now have the velocity of both the star and the planet, meaning this is basically now a spectroscopic binary. You have the velocities of both stars, and therefore you can solve for the masses of both planet and star only using Newton's laws. Also what we see is that this is small average. This is only a 2 sigma measurement. There has been more recent work of other groups. We see that actually this signal is a little bit blue shifted by about 2 kilometers per second with respect to the rest frame of the star. And we think, although the evidence is weak in this case, that this is caused by when this planet moves in front of the star. If this is the star, then the hot day side is on this side, the cold night side is on that side, and we probe an annulus of atmosphere. And because it's warm here and cold there, you actually expect a global wind blowing from the hot day side to the cooler night side, giving a blue shift in the ring of the atmosphere that we actually observe. So this is also the first evidence of seeing some of the atmospheric dynamics of this system. Now, what we did here is then, so this was for the transit measurement. Now we went for thermal emission. As I already explained, we don't need transiting system, and that's good because we can go to a more nearby system. This is the most nearby hot Jupiter we can see from the VLT. And basically we do the same method, but now we don't know the inclination of the system. We observed it for 3 nights. So I think we used the VLT, an 8-meter class telescope, for 3 nights to look at the 3.5 magnitude star. And this is basically the similar diagram. This is again the cross-correlation measurement as function of time. These are the 3 nights. This is velocity, and you have to squeeze your eyes a bit. Therefore, I have this guiding line. But here you can see the actual planet signal of carbon monoxide moving from about plus 80 kilometers per second to minus 80 kilometers per second around the star. You can see it better in the actual rest frame of the planet here. Now the individual spectrum give about measurement of about 1 sigma. So you want to add up the signal as function of time to really get the overall carbon monoxide signal. And the way we do that, because we don't know the inclination, if the inclination is very high, the change in the radial component is large, so you would expect a signal which goes like this. If it's almost a face-on orbit, we get a signal which is like that. So we can add up the velocities in different ways in that way, and we can presume as if we don't know what the system velocity of the star is, so we can add them also up in this way. So this is now for different inclinations and for different system velocities. Now we see a very nice signal here. It's about 6 sigma, and it is actually right at the known system velocity of this star. Now, since then, we have done a handful of these hot Jupiters. The nicest one is, of course, the mother of all exoplanets, planets 51 Pec. It actually turns out it has an inclination which is very high, so it's actually almost an actual transiting system. It probably only misses the transit by a few stellar radii. Now, I don't want to go because I don't have time. I'm skipping a few things. This is a Japanese group who has done some very nice work on TIO in the optical. This is when you actually inject a spurious signal, a fake signal, but you can see here the actual real signal in the data. And the nice thing is that this is actually this molecule was actually expected to be present in these very hot Jupiter atmospheres, but it had never been seen. And what is very nice, you see this molecule in actual emission. So they see emission lines, and that means that there is actually a thermal inversion in this very hot planet, WASP 33. Okay, for the last part of my talk, I want to look a bit more in the future, and that is really, as I just said, we used the VLT 3 nights to look at the 3.5 magnitude star. It shows you that this kind of science is really photon limited, and a larger telescope therefore really helps. So we are very much looking forward to the ELT, and there's a whole interesting suite of science cases that you can actually do. Something we have been looking into very recently is, for example, what kind of isotopes can we actually look for. We are now inclined to actually say that even for Proxima b, we could maybe do, for example, the HDO over a water ratio. That could tell us something about the history of the atmosphere and the planet. Of course, if actually water exists on such a planet. But there's one science case that I want to highlight, and that is maybe the ultimate science case, and that is looking for molecular oxygen in the atmosphere of an Earth-like planet. Now, what kind of signature do you expect? Actually, oxygen is a very nice molecule to actually do this for, because it has these, it has a very nice and regular spectrum. This is the 7600 angstrom band. Anybody working on galaxies always thinks this is a real nuisance. It's not. It's a beautiful band. You can really use to do some very exciting science with. So you can easily calculate what if the Earth would actually transit another star. How would what would the absorption of oxygen look like? So this is now again the effective radius of the planet as function of wavelength, and you get typically lines or absorption would go up to about 85 kilometers, and that's I think that's the beginning of the mesosphere, where the molecular oxygen breaks up, and therefore there above that there is no more oxygen. There's also another interest. So this is 7600 angstrom. There's also at 1.3 micron. There is another oxygen band which can be very useful for the redder stars. So what we did a couple of years ago is to go through the numbers and see purely from a photon counting point of view what you could do with the ELT. And what we did, say there is a nearby M5 dwarf, so say Proxima-like star, and it has a transiting Earth, then what kind of, then you can calculate what this 85 kilometers in change in radius gives you in absorption, and you get signals which are about 5 times 10 to the minus 5. And that's actually not so bad, because if you, this is a model of the CO signal we already saw in tau Botus B, and it's about a factor 3 larger. So we only have to look for a signal which is a factor of 3 smaller than the signals that we actually already see. The only caveat here is this is a magnitude 3.5 star. Oh, this star will be a lot fainter. This will be magnitude 11. So we need a much bigger telescope to actually do this, and we can go through the actual numbers. So let's start here. Say that first we assume that all stars have planets in the exohabitable zone. So there's kind of an upper limit. We know the radius of the star, the mass, where the habitable zone is, how long a transit lasts, and also then we can calculate, we can estimate, okay, at what kind of magnitude do you expect the first transiting system to actually be? Now, that's for M5, that's about magnitude 11. And what is the contrast of the lines? 5 times 10 to the minus 5. What is the signal to noise? And you get with the ELT on one transit, that is actually about 1. So you need to add up about 25 transits or so to see a signal. Probably from one side on the Earth, you can see a few transits per year. So we're talking about a project, a PhD project of about 5 to say 20 years or so. So this is sort of at the limit what you could do. I think this is not a decade of observing time. This is during the course of a decade, 25 nights of actually observing time. Now, what you can also immediately see if you go to sun-like stars, actually the stars are much brighter, but the contrast of the lines are much smaller, but the signal to noise that you get per transit is about the same. But yeah, transits only happen once a year. You have to be lucky that the transit happens just when the sun is down, the star is up, and it's not actually clouded here. So you need about 100 years to actually get to. So this is, I think it's really out of the question that you can do this kind of transit search for molecular oxygen on solar type stars. Now recently we have now, of course, we have now objects. For example, the TRAPPIST-1. It's a bit fainter star, but the actual star is significantly smaller than an M5. So the signal is higher. The signal to actual noise is a little bit lower than 1. So we would need about a 5 to 10 year project to actually do this. But I haven't gone through the numbers yet. But actually, this other oxygen band is probably better because the star is actually a factor of 10 brighter. So we can actually make this a bit shorter. So I think actually that the ELT, when it would have a high resolution spectrograph in the optical, for example, high res, that maybe in a few years, adding up the exotransit signal, we would be sensitive to actually molecular oxygen in this system. Okay, for the how long do I have left, Matt?
5 minutes or so.
5 minutes. I go really fast now for the last bit, and that is, so I talked about the high dispersion work with exotransits. Now I want to end with the high dispersion work with direct imaging. So what is the idea here? The idea turns out to be quite old already. Sparks and Ford in 2002 already worked on this actual idea. What this idea is as follows. So this is a direct image I got from Google. Here is the planet. But you see all these blobs here, which come from the exostar. But yeah, you would like to find planets here. But it's very difficult to see difference between these speckles and an actual planet. However, if you have spectral information, then actually you would see what light is coming from the star and what light is coming from the planet. Because the star, in general, the star light will have a very different spectrum from the actual planet light. So we can use that to probe down into this stellar halo and search for planet spectrum light that basically look like that looks like the spectrum that you actually expect. So, just to show an example of this, this is one of the most famous directly imaged planets, Beta and Pig. And I showed this example for a resolution which is much smaller at 4000, and that's because yeah, we don't have integral field units yet at a resolution of 100 to 1000 that can do this, but in the future MATIS, one of the 3 first light instruments on the ELT, will have a resolution of 100,000. So that instrument will be able to actually do that. So this is the white light image. Actually the adaptive optics system of Symphony is not so good. The planet is somewhere here, but it's completely swamped by the exostar light. But we do have spectra of all these pixels. And we know the star spectrum very well because it should be everywhere the same. So what we do, we actually remove everywhere the starlight. And in the residual spectrum, we cross-correlate with the expected planet spectrum for beta Pig. And what you then get is this bit of magic. This is where planet light seems to be hiding. And you see very nice the beta Pig planet coming out. The contrast changes from 250 to about 100,000. What we also see, this is for a specific model, which is closest to what we expect for the exoplanet. When we move away from this model, we see the signal becoming weaker. So we're also sensitive to actual specific planet parameters. Okay. So actually before that, this was just an example to show how it works. Of course, we don't have an integral field unit to do this at a resolution of 100,000, but we do have the cryo spectrograph with a slit. And if we know where the planet is, we can just put this slit on the star and the planet and see how well it actually works. And this is a planet in an orbit about 20 years. It's a bit about an order of magnitude more massive than Jupiter. This is now the position on the exoslit. We have the star. We know where the exoplanet is. It should be here. It's completely dominated again by the starlight. We actually remove that as well as possible. This is, these are the residual spectrum, and now we cross-correlate each of these residual spectrum with a carbon monoxide template, and what we get is this. This is now the velocity of the carbon monoxide. This is the position on the slit. At the star position, we don't see anything. Of course, we have actually removed everything from the star. At the planet position, we see a very clear carbon monoxide signal. First of all, it is redshifted by about 15 kilometers per second. That's the orbital motion of the planet around the star. And what we see is that the carbon monoxide signal is quite broad. It's broadened by about 25 kilometers per second. And we think this is due to the spin velocity of this planet. That's because of the rotation of the planet. And because we sort of know what the radius is, we can derive that the length of day on Beta Pictoris is about 8 hours. Now, this is a very fast rotation, but if you look at the planet's mass in the solar system as a function of the spin velocity, you see there is actually an actual relation, and Beta Pic just extend this relation to actually higher masses. This is some ideas we have about how planets can actually get spin, but I don't have time. You can ask me later. Yeah, one of the top science cases for MATIS is to actually do this on nearby planets, and we can really push this to rocky planets. This is, as an example, this is one night of observing of super Earth. If Alpha Centauri would have a super Earth, what we now have, this is the eye view of MATIS. We have the two axes here, which is the angular position on the sky, and this is velocity. At the star position, it's of course very noisy because of all the photons from the star, but also at velocity 0, it's very noisy, and that is because we look for spectral features which are the same as the spectral features in our own atmosphere. But because of the radial velocity of the planet, it's actually offsetted, and therefore you can see the exoplanet. And if we would observe now a few months later, it would not only have moved in the sky, but also the radial velocity would have changed. So you can also map out the actual the radial velocity orbit of this planet. Now, so this with the first light instrument MATIS on the ELT, we will be able to actually do this. Hopefully not long after first light. What we really want to do is to move this to the actual optical to look for reflected light, to look for oxygen, and then we really have to try to understand how to actually do this. And I think therefore a very important project is led by Christoph Lovis to actually try to couple the sphere instrument with actual espresso or a similar instrument to get this the high resolution capability on a sphere to actually test this. One of the things he had been going through, I think this will be very difficult, but he claims if we can do this well, we could actually measure reflected light on Proxima b in about 30 nights. I think this will be very difficult, very challenging, but I still think it's very important because this really will teach us how to actually do this. There are a lot of different instruments now, also in Keck and Subaru, that are building instruments that are going to actually do this. And I think that's really important because you have to realize that this method scales, the actual exposure time needed scales with the diameter of the telescope to the 4th power. So if we can almost do this with the VLT, coupling sphere to a high dispersion spectrograph, with the ELT, we could in principle do this a factor 500 or so faster. So 50 nights suddenly only become a few hours. And then a kind of observations which you could expect, this would be Proxima b in reflected light. Here is a star, here is the actual planet. So this is hopefully in the future, before I grow really gray and old, we will be able to actually do this. Thank you.
Yeah, so super interesting. So it's interesting what you say about how it's important to collect photons. So can you just make a general comment about space-based detection of exoplanet atmospheres, perhaps with coronagraphic methods? Like the terrestrial planet finder, that's no longer on the cards, is it?
No, that's no longer on the cards. So there are two new studies that NASA is doing. There's the HABEX telescope, and there is the LUVOIR telescope. So one is a more a general purpose telescope that can also do exoplanets, and HABEX is really the one that tries to only focus on exoplanets. Their wavelength ranges are slightly different. Yeah, what I think is the actual relation between the ELTs and those kind of space missions is with the ELTs we will really do our best to try to image and to really study the most nearby planets. We will be able, for example, to do Proxima b, maybe some other very nearby M dwarfs. Maybe one of the solar type stars we can do one or two planets on, but it will be a very limited sample. Because as soon as you go a factor 2 further away, factor 4 fainter signal, factor 16 longer exposure, this becomes terrible, right? So if you then, and what I started my talk with, measuring molecular oxygen is not enough. You have to understand what's happening on this planet, and for that you need to have samples of planets. So I think for the next step, you really want to have a large space mission to be able to probe samples of 50 stars or so. And for example, then the HABEX or the other one, LUVOIR, could actually do this. Yeah.
If you were observing the Earth, in good condition, maybe around Proxima, would you be able to see methane, CH4?
Yes, yeah, I think so. That will, for example, be in the METIS wavelength range. That should be a lot of methane. So I think, for example, methane should be easier than for example, molecular oxygen.
It will be easier?
Yeah, I think it will be easier if it has methane and if the absorption is strong enough, we should be able to see
but
this.
at the level of methane in our own atmosphere, which is a few ppm only.
Yeah, so, but the methane absorption is already very, very strong. So we can actually, the regions where you expect the strongest methane absorption, we just cannot actually use because you don't, it's completely opaque in our own atmosphere. So we actually, although the volume mixing ratio is very low, we already have to go to spectral regions where the actual absorption is weaker to be able to actually see it. But I think that molecules like the first molecules we can do on rocky planets will be water, CO2, and methane. I think those will be the easier, between quotes. Yeah. Oh, and of course, molecular oxygen is more difficult because it is in the optical. So any adaptive optic system, and therefore it's much more difficult in the optical than we can do in the infrared.
You didn't mention what we have learned from the observation of the atmosphere of hot Jupiters. Have we learned anything about their formation, their history, their evolution, or something? If it is possible, I know that it's probably a topic for another talk, but if you can.
Yeah. So you have to realize that the first measurements on the atmospheres of hot Jupiters are quite recent, right? So we started, I think, or people started in 2002 when they measured sodium, yeah, and then now since a few years they can do water. We have some carbon monoxide measurements. All those measurements are not very surprising. There is, of course, this is a hot hydrogen-dominated atmosphere. There should be water, there should be CO. So in that sense, I don't think we have learned much yet really about the atmospheres or the atmospheric physics. We have, I think, what I showed about David Singh's work, about this correlation between the water signature and between the hazes. I think this is the first time that an observation is really telling us something physically, what's happening in the atmosphere.
For instance, the observation of titanium oxide, can it teach us something? Can it say something that the mountain, in fact, is probably evaporated and what we are seeing very closely?
Well, of course, M, the dwarf stars, and brown, the dwarfs have this molecule. So it's not surprising that TiO is actually present in these atmospheres. It has been searched for a long time because there was evidence, although the evidence had been before quite weak, that these planets have inversion layers, and therefore some molecule or species has to actually absorb the starlight high up in the atmosphere to heat the atmosphere. And TiO was seen as one of the possible molecules to actually do this, and it had been searched for a long time, and it was not seen. But now only when people go to the very hot planets, they are the one example I showed you is the most hottest planet known. That is actually the first time that they actually see this molecule. So we start to learn something about the atmospheric physics of planets. But to link that to how these planets are formed, that's still a question which is much further in the future, I think.
Jean-Pierre.
So what you have shown, so by using high contrast imaging, so that I think so ideal situation, so because we are back to what we're doing, observing the solar system, so you can look directly to the planet. But I was somewhat surprised that, of course, high spectral resolution, that also is ideal. But we learn also many things because it's quite faint in any case. And so high spectral resolution will be always on a very limited cases. So why don't use a low spectral resolution, a broad spectral range?
Yeah, so this is an aspect I have not really talked about. The problem is, so when you take your telescope to space, please do not actually do this work. Yeah, a low resolution spectrum is fine, and please use actually that, because yeah, you spread out your photons over a very large number of pixels. That doesn't help you observing faint targets. However, observing from the ground, using a low resolution spectrum or even just imaging or in a filter band is very difficult because of the Earth's atmosphere. So we are looking at, if you now do not think at the direct imaging case, but at say the transit case, yeah, you want to see variations in the photometry on the level of 10 to the -4, right? And just observing with your telescope to a star is not going to do that because the actual atmosphere fluctuates at significantly higher level. So what you can do is to have an external reference star and see the actual difference in flux, but also to do that at 10 to the -4 level is very difficult because differential atmospheric effect, but also the two stars, they follow different paths within your instrument, and and therefore have actually different effect. If you now go to the very high spectral resolution, and maybe I can show you this, for example, with this spectrum, this really helps because we're not interested in what the continuum is doing. We don't measure that. We only measure the contrast of the actual lines. So one wavelength we have a strong absorption, the next wavelength we don't have absorption. And anything the atmosphere is doing is not changing from one wavelength to the actual next. These are all except for the Earth's atmospheric lines. Basically, from one wavelength to the next, the atmosphere, the throughput of the atmosphere is the same, and therefore you can actually use this. Yeah.
Last question.
My question is connected to this high-resolution spectroscopy. What typical broadening of line do you expect for these lines? Is it dominated by collisional broadening for atmospheric exoplanet atmospheres, or typical values? What is
this really depends on what kind of measurement you actually do. This is you actually expect. This is a typical profile if you would have a non-rotating planet. This dashed line here is what you expect, and that is caused by the fact that away from the center of the line you just probe deeper into the atmosphere with higher pressures, right? And that basically gives you the actual broadening of the actual line. So in this case, because the planet is spinning, that is actually dominating the broadening of the actual line. But if you would go to Earth-like planets or even the hot Jupiters, which are locked, they actually rotate a lot slower, so you wouldn't see the actual rotational broadening of the planet. Does that sort of? Yeah, I'm just thinking now what is causing this broadening. Is this collisional broadening, Matt? Probably, yeah. I'm not sure.
How much resolution do you need? Maybe you just can stay with available 50, 100, 1,000 of resolution.
Yeah, so we have been doing this so also at lower spectral resolution, so even down to 5,000. But then the contrast of the line become a lot smaller. So you really lose a lot of signal. In principle, you're going from 100,000 to 50,000. Your lines become less deep, but I think that the method still actually works. Although the removal of the Earth's atmosphere already becomes a bit more difficult. So, and if you really go significantly at Keck, there is the NIRSPEC that uses a resolution of 25,000. You can already see with that instrument they actually have a lot more trouble of doing this work than we have.
Our atmosphere has all these in it.
Yes. Yes.
Okay, so let's thank Ignas again.
Thank you.